Welcome back to multivariate calculus. In this video, we're going to be looking at parallel and perpendicular vectors. We've seen previously that using the dot product, you can determine whether two vectors are parallel, perpendicular, or neither. And that's fantastic, it's very useful. But the question we're going to ask today is slightly different. Given things that we know about vectors, can we determine a vector which is parallel or a vector that is perpendicular? And it turns out that that's fairly straightforward. So let me get my head out of the way and let's jump right in to our first theorem. So let's consider vector u, which is given in component form with components x, y, and z. I claim that every vector which is parallel to u can be written in the form kx, ky, kz for some constant k. Right. So in order to prove this, I need two different things. First of all, show that these two vectors are in fact parallel to each other. So let's take x, y, z and dot it with kx, ky, kz to get kx squared plus ky squared plus kz squared. Then let's find the magnitude of x, y, z as the square root of x squared plus y squared plus z squared. And let's find the magnitude of kx, ky, kz as the square root of k squared x squared plus k squared y squared plus k squared z squared. And then let's play around a little bit. Notice that there's a common factor of k here. I'm sorry, of k squared here. And I can take that k squared out of the square root and just get, I guess it's the absolute value of k, right? Whether k is positive or negative will change that. So when I multiply these two things together, I get the absolute value of k times root x squared plus y squared plus z squared times root x squared plus y squared plus z squared is just x squared plus y squared plus z squared. And that absolute value means there's a plus or minus. Otherwise, I can just distribute and get what I got with the dot product. Kx squared plus ky squared plus kz squared. All right. So notice here that I have proven that every vector written as kx, ky, kz is parallel to x, y, z, but I haven't proven that every parallel vector can be written like this. The second half of the proof is incredibly tedious. I don't think it's very interesting. But even with just that, let's consider vectors that we looked at previously. Right? We saw the vectors, I've already forgotten, 4, -2, 6, and -6, 3, -9, if I remember correctly. And notice that this one is -3/2 times 4, -2, 6. So just with that, we can start thinking about parallel vectors, and we can build up our parallel vectors by using multiples. And that's really what I care about in this course. Given a vector, find another vector parallel to it by using this trick of multiples. We actually used that idea already talking about the projection, kind of hand waved past that quickly, but here's where that comes from and why we know that's going to work. Perpendicular is a little bit more of a challenge for several reasons. The first of which is that there are just too many perpendicular vectors. Given a vector, hold on a second. Yeah, the black pen will work perfectly. It won't blend into the black background at all. All right, blue pen. Blue pen is a vector, and it mostly shows up on the screen. Given a vector in 2 dimensions, perpendicular vectors are easy, right? In 2 dimensions, we have a vector pointing like this, and there's a perpendicular vector that points like that, and there's a perpendicular vector that points like that. And that's it in 2 dimensions. In 3 dimensions, I can also have a vector that points like this, or like that, or like that. Anything in this entire plane that is my hand is perpendicular to the vector. So talking about a vector perpendicular to one vector is not sufficient. It doesn't give us enough information to do anything interesting. Instead, we want to find a vector perpendicular to each of 2 other vectors. And even at that, there are 2 options, so we have to make a choice. And we're going to make the choice following the right-hand rule. Depending on the order that we name the vectors, we're going to take our right hand. I'm in mirror mode, so I know this looks like my left hand. But I'm going to take my right hand, and I'm going to make the 2 vectors, my pointer finger and my middle finger, pointing in opposite directions. The way that I can actually make that work, there's always some way you can make it work, right? And then the perpendicular vector will point in the direction of my thumb. And so we're going to define what's called the vector cross product u cross v so that it is perpendicular to u and perpendicular to v. And we'll choose the branch of this which follows the right-hand rule. We've so far only used the right-hand rule to talk about our coordinate axes. And since that's what we know, let's start there. If we took I hat cross j hat, that's the vector in the x direction cross with the vector in the y direction, we should get the vector in the z direction k hat. And if we did it in the other order, we would flip our hand upside down, which means that j hat cross I hat should give us the negative of k hat. right? If you try to flip around and instead of having, if you have x and y oriented like that, then z would be oriented upward. But if you did it the other way and you had x and y oriented like that, then z would be oriented downward and the negative z axis would be upward. And that's what we're describing right here. Likewise, for the other combinations, if we took j hat cross k hat, we should end up with I hat. And if we took k hat cross I hat, we should end up with j hat. And if we did either of those things backwards, we should get the negative. Right. Last thing we know is that we are going down this route because if we take a single vector, it doesn't give us enough information. We need two different vectors. So if we take I hat with itself, we don't get enough information. That's not useful. And so we'll get 0 out from that. Likewise, j cross j and k cross k will all give us 0. All right, so the cross product is not commutative. It's anti-commutative, the same way subtraction is. You do it the wrong way, you get the opposite of the answer. And that's going to be important for us. And with those 9 operations, we'll define the cross product. And I claim that just adding one more piece will make things work really nicely. I want to make the cross product distribute. There is nothing here that is obvious as to why that should give us the perpendicular vector we're after. So this is kind of a revisionist proof. Rather than develop the cross product and see why it works, or rather than develop the cross product in a way that demonstrates why it works, I'm going to demonstrate how it works and then go backwards and verify that it does work. It's a less rewarding way of proving something, but especially for this level of math class, a sophomore year mathematics course, looking at things in this perspective allows us to talk about the interesting properties of things like the cross product without getting bogged down in too much detail. So if I get my head out of the way and I look at a couple of vectors, we should be able to perform a cross product by following that rule. So consider vector u. The same way I've done before, it's going to be ux in the I direction, uy in the j direction, and uz in the k direction. And then we'll have vector v, which is given as vx in the I direction, vy in the j direction, and vz in the k direction. And if I take u cross v, that is the cross product in all of this, uxi plus uyj plus uzk cross with vxi plus vyj plus vzk. And here's where things start to get messy because I am going to distribute. I'm going to take uxi and I'm going to cross it with each of these. Then I'm going to take uyj and cross with each, and the same thing with the k1. So we're going to get uxi cross vxi. We're going to get uxi cross vyj. We're going to get uxi cross vzk. Then we'll take uy. So we get uyj cross vxi. Uyj cross vyj. And uyj cross vzk. And then we do it with the z component. uzk cross vxi, uzk cross vyj, uzk cross vzk. And component by component, we know what the cross products are. I cross I is 0. I cross j is k, so we have ux vy k. I cross k, that's backwards, that's the negative j, so we'll have minus ux vz j. Then we look at the second row and we do the same thing. J cross I, that's backwards, that's going to be minus so I guess I wrote too soon. That's going to be minus uy vx k. J cross j is 0. J cross k is I, so that's going to be plus uy vz I. And then the third row, k cross I is j, so uz vx j. K cross j is minus I, and then k cross k is 0. Now, organize this. Get the components together. So in the x direction, we have uyvz, and we have minus uzvy. That's all times I hat. We have uzvx and uxvz. That's all times j hat. And then we have uxvy and minus uyvx. That's all times k hat. And that's what we get when we perform the cross product. That's the formula that we end up with. I'm going to come back in a few moments and verify that this actually does give us the result we want. I'm going to take the dot product of this thing with u, and then I'm going to take the dot product of this thing with v, and I'm going to verify in both cases we get 0. because two vectors are perpendicular if and only if their dot product is 0. But before I do that, I want to at least mention, if you have worked with matrices in the past, and you have seen the idea of the determinant of a 3 by 3 matrix. Specifically, I want to look at the 3 by 3 matrix, which in the first row has I hat, j hat, and k hat. In the second row has ux, uy, uz, and in the third row has vx, vy, vz. If you already know how to calculate the determinant of a 3 by 3 matrix, I can guarantee you that memorizing that U cross V is the determinant of this 3 by 3 matrix is easier than memorizing the formula that I just wrote down. If you have not seen how to calculate the determinant of a 3 by 3 matrix, this might still be easier to learn than to memorize that formula that I just wrote down. But to calculate the determinant of a matrix, you expand on a row, and you take, for each entry, everything that does not share the row and column. So I hat gives you this 2 by 2 matrix. J hat gives you this weird 2 by 2 matrix if you leave all that out, and then k hat is a relatively easy one. And you alternate between addition and subtraction. So it'll be I hat times the determinant of the 2 by 2 matrix if you eliminate the row and column that have I, uy, uz, vy, vz. Alternating sign, so minus j hat. If you eliminate the row and column that has j hat, it will be ux, uz, vx, vz. And then alternating sign, this will be plus k hat times, if you eliminate that row and column, ux, uy, vx, vy. And then to calculate the determinant of a 2 by 2 matrix, you take the diagonal entries and multiply them. Downward diagonal minus upward diagonal. So we get I hat times uyvz minus vyuz minus j hat times uxvz minus vxuz plus k hat times uxvy minus vxuy. And you can verify that if you just play a little bit of algebra games rearranging, you get back to where we started. This has nothing intrinsically to do with the way that matrices are defined or the way that the determinant of a matrix is defined. This is almost entirely coincidental. It's a useful mnemonic device for remembering how this works. Like I said, if you've learned how determinants of matrices work, this is an easy way to remember how to take a cross product. If you've never learned how determinants of matrices work before, it may or may not be useful for you to learn. If you are looking at moving ahead and possibly eventually taking a course in linear algebra, learning how determinants of matrices work is going to be very useful to you, and I encourage you to try to use that definition. But I'm not going to push it. However you can remember how this works is perfectly fine. But let's take a look. I said that I was going to take a look at the dot product of u dot u cross v. And I'll use this second version of it. It's mathematically equivalent, just written a little bit differently. I'm using that one just because it is still on screen. So the x component will be ux. We'll multiply it by the x component of this thing, which is uy vz minus vy uz. And then we have minus, because there's a minus here, uy times ux vz minus vx uz. And then we have plus uz times ux vy minus vx uy. And I'm going to rearrange this as I distribute so that I always have x, y, z, and I always have u before v otherwise. I don't think that ever comes up. I think that everything has exactly one x, exactly one y, exactly one z, and it's just a matter of whether it's u or v. So rearranging everything so it's always x, y, z, and distributing, we get ux, uy, vz minus ux, vy, uz minus ux, uy, vz minus minus is plus vx, uy, uz plus ux, vy, uz minus vx, uy, uz. And now let's cross our fingers. We've got ux, uy, vz. Positive and negative cancel each other out. We've got ux, vy, uz. Negative, positive cancel each other out. We've got vx, uy, uz. Positive, negative cancel each other out. And so we can verify that by using this process, we will always get something that's perpendicular to u. I encourage you to work through and show that it also works to always give you something perpendicular to v, but for the sake of space, I'm not going to. Instead, let's dive in and actually perform one of these calculations. So if I have two vectors, let's take a look at, say, 3, -2, 4, that I'm crossing with 5, 1, -7. You can set this up in either memorizing the formula or using the determinant. I find using the determinant to be far and away easier. Again, if you know the determinant, it's always easier. If you don't know the determinant, sometimes it's easier, sometimes it's not. But let's go ahead. This is going to be first row, I hat, j hat, k hat. Second row, 3, -2, 4. Third row, 5, 1, -7. And expanding that, it's going to be I hat times the 2 by 2 matrix, -2, 4, 1, -7, right? Remove the row and column that have I in it. Then minus j hat, remove the row and column that have j in it, 3, 4, 5, -7. And then plus k hat, remove the row and column that have k in it, that's 3, oh boy, sorry about that, 3, -2, 5, 1. I'm running out of space. I can just barely squeeze that in there, but that works. And then take all of those 2 by 2 determinants. So we have I hat times -2 times -7 is 14. minus 1 times 4 is 4, minus j hat, we have 3 times negative 7 is negative 21, minus 5 times 4 is 20, plus k hat, 3 times 1 is 3, minus 5 times negative 2 is plus 10, right? Minus a minus there. And so we have 10 I hat minus 21 minus 20 is minus 41, but then we have a minus in front, so that's plus 41 j hat and plus 13 k hat. Right. I'd like you to try a similar problem. 3 I hat minus j hat plus k hat cross product with I hat minus 2k. Too many k's here, not enough j's. I hat minus 2j hat plus 3k hat. And see what you can do with this one. Right? Calculate the cross product of the two vectors. If you really want to be ambitious, go into GeoGebra and plot the three vectors and verify for yourself that the result is in fact perpendicular to each of the ones you started with. I'm not specifically requesting that, but if you want to play around with GeoGebra's 3D plotting, that might be something fun to do. I'm a mathematician, I have a skewed definition of fun. Regardless, spend a few minutes, see what you can do with this problem, and I'll see you for the next video.